All right. So yeah, I was briefly disconnected due to my internet issue here, but finally I'm back. Thanks for staying in. So let's take a look on the solutions together now. I think I saw some responses in already. So let's take a look on the solution together. All right. So as you can see, um, before the collision, all right, and then after the collision. So after the collision, the two are moving in two-dimensional plane. So this is two-dimensional collision, and we can apply conservation of momentum in x direction and then conservation of momentum in y direction. Okay, so these are the two equations to start with. So then you basically, so this is similar to when you do collision in one dimensional, but you just expand it to two dimensional. Okay, so then you just do x direction and then repeat it for y direction. Okay, so you want to start with initial momentum, so it will be m1v 1x. All right, now it says the two parts are identical, m1 equal to m2, right? So then let's just use the same mass m for the two parts. Okay, so m1 is m, m2 is also m. Okay, so then you can say m v1x plus m v2x, right? That should be equal to m v1x prime. So prime means final plus m v2x prime. Okay, so this is the first equation, comes down here. And then the second equation in the y direction, momentum should conserve as well. So m v1y plus m v2y equals to m v1y prime plus m v2y prime. Okay, now you probably realize that the mass is the same overall. So then actually the mass doesn't really matter, right? So, and the problem didn't give you the mass of the two parts. So that's fine because it's not a deciding factor. Or actually it will cancel out here. So you can see from both equations, the mass will cancel out across because you have a mass on each of the terms. Okay. So then basically, instead of looking at the conservation momentum, you're actually looking at the velocities in the x component and y component. Okay, so let's see. Um, now there's this guy here. V2 is initially 0, so then its x component should be 0, y component should be 0, right? So this guy goes to 0, this guy goes to 0. All right. V1 is along the x direction, so you can take the original direction to be the x direction and then perpendicular to it to be the y direction. So then V1x, this guy would be 6, right? So then this would be V1x. V1x is 6 meters per second. V1y should be 0, okay? So then this is 0. V1y is 0. This guy is 6. All right. It tells you V1 prime is 5.2 and then it has an angle of 30 degrees with the x direction. So then V1 x prime should be V1 prime cosine of the angle 30, right? V2 or V1 again, the y prime should be V1 sine of the 30 degrees, okay? So these are the a few knowns we already have here. It's now asking what would be the V2 prime, the magnitude, and then the angle theta. Okay, so now we can write V2 prime, the x direction, as V2 prime cosine of theta 2. Okay, the angle theta 2, and then V2 prime y would be V2 prime sine of theta 2, right? With this one and this one being unknowns. Okay. And then we will have two equations and we have two two unknowns, and we should be able to figure out both of them. Okay, so now let's take these expressions or the numbers into those two equations. So v1x is going to be 6, all right, meters per second plus 0 that equals to v1 x prime. So v1 is 5.2, so then 5.2 meters per second cosine of 30 plus V2 prime x will be this guy, v2 prime x. So v2 prime cosine of theta 2. Okay, so that's the first equation. The second equation then will be 0 equals to v1 y prime, v1 y prime. So v1 prime sine, or that's 5.2, sorry, 5.2 meters per second sine of 30 plus v2y prime, which will be v2 prime sine of theta 2. Okay, so you have these two equations, and then you have two unknowns in them, v2 prime and then theta 2, v2 prime and theta 2. Okay, so then you can solve for both of them. All right, so let's see how you can solve both of them. So you can write one unknown as a function of the other one. Okay, that means in terms of the other, and then replace it in the second equation with the expression. Okay, so let's take a look. Okay. Oh, I think you can actually I can do this in a different way. Okay, because yeah, you can do this way. There's no problem with that. Okay, so you can do that, or you can do it this way. I just realized you can do actually do this one in the easier way. So again, take a look on this one here. In this case, we do not substitute those two. Okay, let's not do substitution of those two, but you'll see what I'm talking about. So if you write the two equations, 6.00 meters per second equals to 5.20 meters per second, right? Cosine of 30 degrees plus, still keep the v2 prime in x direction, okay? And then this one equals to 5.20 meters per second sine of 30 degrees plus v2y prime. Okay, so then you can actually solve for v2 prime x here. So that means x component of the final velocity of the v2. And then you can also solve for the y component of the final velocity of v2 here, right? Then these are the two components of the velocity, final velocity of the v2 prime. Then using the components, you can calculate magnitude and then the directional angle, right? Because this is a velocity, it's a vector. Given their components, you can solve for their magnitude and then the directional angle. Okay, so let's do it that way. So then v2 prime x is equal to, so this guy here, right? So if you're looking for this one, you kind of isolate this guy to just right hand side equation, move this guy to the left. So it'll be 6.00 meters per second minus 5.2 meters per second cosine of 30 degree. That will give you 1.497 meters per second. Okay. Now, then similarly, you can do for this guy, the v2 y prime. So then it will be isolating this guy, right, to the one side equation and then move this guy to the other. So minus 5.2 meters per second sine of 30 degrees. That will be negative of 2.600. Okay. So the problem gives us like 3 sig figs. We want to keep 4 sig fig while we are doing the work here. All right, so then you have the two components, x and y component. You can calculate for the magnitude. Okay, so v2 prime, the magnitude, then should be square root of the x square plus the y component square, right? So 1.497 meters per second square plus minus 2.600 meters per second square, and then take square root of it. Okay, so this will tell you v2 prime, the magnitude is going to be 3.00 meters per second. Okay, so that's the magnitude. Now the directional angle theta 2 then should be tangent inverse of y divided by x. Okay, so tangent inverse of minus 2.600 meters per second divided by 1.497 meters per second. Okay, that will give you roughly minus 60.0 degrees. Okay, so you have the magnitude, you have the angle, directional angle. All right. So let me know if you have question with part A. If it's clear, then we can take a look on part B. Part B is asking you to verify that the collision is elastic. That means you want to check if the kinetic energy initial is equal to kinetic energy final. Okay, so part B, we are going to check on kinetic energy initial, KE initial, and then KE final, and then to see if they are equal to each other. All right. So kinetic energy initial will be 1/2 m1 v1 square, right? m1, m2 are both m, and then 1/2 m2 v2 square. And then again, we know that initially v2 is 0, so this guy is 0, okay? And this is 1/2 the mass times the initial speed, 6.0 meters per second square, and then squared, oh, per second, just per second, and then squared, okay? Now, the mass is not given, so you will just express the kinetic energy in terms of mass times the numbers, okay? So this will be 36, 6 squared will be 36, and then 1/2 will give you 18. So you can just write down 18 times the mass, okay? So keep in mind this is mass, all right? So we'll just leave it over there because the mass is not given, okay? Now, that's your initial kinetic energy. Final kinetic energy should be 1/2 mass v1 prime, the final speed square, plus 1/2 m v2 prime, okay? So this would be then 1/2 the mass v1 prime is 5.2 meters per second, okay, square, and then plus 1/2 mass of 3.00. This is from part A. We solve for the magnitude of the velocity, okay? So again, you'll just express that this in terms of mass, so numbers times mass. So this guy 1/2 5.20 square, okay, plus 1/2 3.0 square, okay, and then multiply by mass. You got kind of single out mass because mass is on both terms. So plugging these numbers into your calculator, you'll also figure out this is going to be 18, equal to 18 times the mass, okay? So then that's consistent over here, 18 mass times mass, and then 18 times mass over there, okay? Initial and final, so they are actually equal to each other. So initial then equal to final, okay? So then collision is elastic. Okay, that means kinetic energy is conserved. All right. Okay. So if that's clear to you guys, we are going to move on here. So we'll look on the next section, rocket propulsion. Okay, so there's a video here. I want to share with you guys the video. Okay, so let me just do a new share here, and let's see. Let me stop share and then reshare because I'm not sure if I have shared correctly. All right.
And there you can see on your screen as they're coming through the crew access arm, entering the white room right before they are able.
About 30 minutes ago, we're back with some live video here. The team was able to close Dragon's hatch with Bob and Doug safe inside. So we are under
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff of the Falcon 9 and Crew Dragon. Go NASA, go SpaceX, Godspeed, Bob and Doug.
America has launched. And so rises a new era of American spaceflight, and with it the ambitions of a new generation continuing the dream. 20 seconds into flight, stage 1 propulsion is nominal.
You want to pay attention to also the right bottom corner here on the speed. Okay, you can see the speed is increasing, so that means there's acceleration.
Falcon power telemetry nominal.
M1D throttle down.
We're throttling down to get ready for the period of maximum dynamic pressure. We're in the throttle bucket. Reports say all systems are go.
Vehicle is supersonic.
We've exceeded Mach 1 on the Falcon 9.
M1D throttle up.
We're throttling back up to full power as we're through max Q.
Copy, 1 Bravo.
Coming up is going to be the triple. We'll have main engine cutoff of the 9 first stage engines, stage separation, and then ignition.
All right, so I think that's enough. Okay. So let's go back to the lecture here. So the video you saw was the SpaceX and NASA their project working together in the over the summer. I actually watched the live video that got me also excited. So I'm sure like some of you guys have watched this. Okay, but this is the topic in this section here. Rocket propulsion. Okay, so actually when the rocket is being launched, so then the fuels in the rocket are inside the rocket are ignited, and then they the reaction of the fuels, the hydrogen and oxygen, they will produce a lot of pressure that pushes the exhaust gas outside. So that's why you see the flames here, and then the gas is being expelled out. Okay. So in that case, when the rocket is being launched into the air, the mass of the rocket actually is changing because you are expelling out the exhaust gas all the time. So then the mass of the rocket is changing. So if you remember for Newton's second law, when we said if you have changing of mass, you can also actually get a result of the force on the object. Okay. So that's the expelled gas over here, which gives the reaction force. So because the rocket has to push the exhaust gas out, okay, so then in reaction to that, the rocket will receive a reaction force, which is called a thrust, okay, of the rocket. So let's take a look at the math here. So the rocket, this is the momentum for the exhaust gas, right? So it's changing in mass. That's the amount of the gas being expelled out times the velocity of it. So that gives you the change in momentum of the exhaust gas. In return, the rocket will receive the amount of the momentum change. Okay, so then the rocket will have momentum change over, say, a particular time interval delta t. So then the thrust force will be equal to delta p over delta t. And if the velocity is not changing for the exhaust gas, then delta m is changing. So this will give you delta m divided by delta t times the v. Okay, so then this is the thrust force on the rocket. Now, of course, the rocket have to overcome the weight of itself. So then F minus mg will be the net force. Okay, so basically F minus mg, the thrust minus the mg will be the net force on the rocket, and then the acceleration will be equal to basically F divided by mass, right? So over this divided by the mass, okay? And then the second term will be minus mg divided by the mass. So then m will cancel out. So then this is the net acceleration of the rocket that is receiving, okay? So delta m divided by delta t times v divided by m minus g, okay? Now, you have this minus g term because its rocket is going upward, right? Straight upward, okay? So that's the concept here. All right. So actually rocket science is not quite terribly hard to understand, right? Yeah, but the design it is very difficult. Okay. All right. So let's see. We'll take one example on the this here. So it says a child sitting in a wagon with a pile of rocks. Each has mass of 0.34 kilograms. So each rock have identical mass. And if she can throw each rock with a speed of 9.5 meters per second relative to the ground, causing the wagon to move, how many rocks must she throw per minute to maintain a constant average speed against a 3.4 newtons force of friction? Okay, I'll give you guys a maybe just say 1 minute to see if you have a plan for this, and then we'll take a look on the solutions together. Okay, for the time constraint. So I can actually draw the sketch over here. So say there's this wagon over here, and then there's a pile of rocks. Okay, and then a child is sitting over here. She throws out rock. Okay, in that way. So if she does that way, then the wagon will receive speed in this direction, right? Okay. So if the wagon goes in that direction, there will be friction force in this direction, and then there will be F of the thrust because she's throwing out the rocket in that way. Okay, for this direction, normal force will cancel out the weight, so we don't have to worry about that. And this guy should also cancel out this, right? Because it says the wagon has constant speed, okay, with a speed of 9.5 relative to the ground. So that's constant speed there. So this is 9.5 constant speed. Okay, so then these two should cancel out. So the force, the thrust force, should be equal to delta m over delta t, right, times the v. If you go one slice back, because force should be equal to delta p. Force is equal to delta p over delta t. So delta p in this case, v is constant, so then it will be the changing of the mass, okay? And delta t, let's take 1 minute because it's asking you how many rocks per minute, okay? So then let's take 1 minute, take delta t as 1 minute, which is 60 seconds, okay? Now, the change in mass, the mass delta m change in mass per minute should be equal to the mass of each rock. Let me call the m naught, m sub 0, times the number of rocks. Okay, let me call it m. So then n is what we are looking for, number of rocks per minute. Okay, so this is the thrust force, should be equal to Fk, the friction force, right? It tells you the friction force is 3.4 Newton. So basically this is 3.4 Newtons because F thrust should be equal to Fk, equal to 3.4 Newtons. Okay. Let me stop sharing the screen so you guys may be seeing a larger screen on your end. Okay. Make sure you click on the speaker view so that you will have a larger view on your screen. All right, so let's see. So 3.4 is F thrust. So you can set up the 3.4 Newtons is equal to delta M, which is M times M naught. M naught is the each rock, mass of each rock is 0.34 kilograms, okay? Times the number of rocks divided by 60 seconds times the V, 9.5 meters per second, okay? So then, now, yeah, this is number of rocks. This is the unit Newton, okay? So pay attention to those two. Do not cancel out, okay? So that's the unit. That's the number of rocks. But so then you solve for n here. Or let's just drop out the units here because we have everything in SI unit. Okay, not confused with the symbol m here stands for number of rocks. So that's equal to, you want to isolate that, right? So put everything to the other side of the equation. Denominator becomes numerator, so 60 times 3.4, okay, and then divided by 0.34 times 9.5, okay. So you'll then get about 63.2 rocks per minute, okay. And then you want to round up, okay, so to be, because you cannot throw 0.2 rocks, okay, so roughly 64, okay, rocks per minute. Now in this case, you don't have the minus g part or minus mg part because your thrust force is in the horizontal direction, okay, but you do have to subtract the friction, okay, for the total force. All right, let me know if you have questions. Okay, so otherwise we are going to just move on here. Now this is not the content in the textbook, but it's actually within the context of the conservation of momentum. Okay, so recoil, that happens when if you fire say a pistol over here, so then when the bullets comes out, it has a momentum going forward. So because of conservation of momentum, then the gun itself will receive a backward momentum, right? Because the final of the two, P plus this minus P, should be equal to the initial of 0. So then this is minus P. So then the gun will move backward, okay? So this is the recoil. It's the term that refers to moment when a gun moves backward after it's shot, okay? If you guys have been in the shooting range, and if you fire a bullet, you will probably receive that recoil force on your shoulder, okay? So the momentum, as I mentioned before, was 0 before the bullet is fired. So then total momentum after, it should be also 0, okay? So you can set that up. Okay, so this is like the backward process of the example we check on Monday, the last one we check on Monday, when the two skaters are pushing against each other, okay? Or about the same concept over there, okay? So they have two objects, initially they are at rest, they have contact or reaction, and then they will separate with momentums in opposite direction, but the same magnitude, okay? Let's take a look on the example on this one here. So it says military rifles have a mechanism for reducing the recoil forces of the gun on the person firing it. An internal part recoils over a relative large distance that is stopped by damping mechanism in the gun. Okay, so the larger distance reduce the average force needs it to stop the internal part. Okay, so what happens is let me draw a sketch over here. So inside the gun or rifle, they were kind of shape. Okay, inside over here, when the bullet is fired out, okay, there's a part over here actually can move through this distance, this amount of distance. Okay, so this is the bullet going out. Okay, and then this guy goes in that direction. Okay, slows down. So it's asking you that calculate recoil velocity of, so this is the plunger here. So this is 1 kilogram. Okay, 1.00. And then the bullet, it says it's 0.0200 kilogram. 1.00. Okay, the bullet is going at a speed of 600 meters per second. It's asking you calculate recoil velocity. So then this is you are just looking at these two parts. Okay, the bullet and this plunger here. So you apply conservation of momentum here. All right, so let me call this m, small m, this is capital M, okay, because this is heavier. And then this as V0. Okay, this is as V. You can be creative with your symbols. Then as long as you know which one is which you are talking about, that's fine. Okay, so then the final mv0 plus the capital MV, that should be equal to the initial momentum should be 0, right? Before the bullet is fired, both are at stationary. So then initial, this is initial momentum, this is final momentum. Final momentum is equal to initial momentum. Okay, so then the velocity for the plunger of this guy, that's the unknown. You want to move this to the other side of the equation. So capital MV equals to small mv0. So then V is equal to small mv0 or minus here. If you move this guy to the other side, it becomes minus divided by capital M. Okay, so minus a 0.02 kilogram times 600 meters per second over 1.00 kilogram. That will give you the recoil velocity of the plunger. Okay, so that's going to be minus 12 meters per second. Okay, so minus sign says it's going backward. Okay, so that's fine. It just indicates the direction. All right. Let me stop sharing so you guys get a better, larger view on your end. On the second part, it says it's asking if this part is stopped over a distance of 20 centimeters. So it says if this is 20 centimeter, it moves over when it reaches here for a distance of 20 centimeter, then it's stopped. So then the final is 0. Okay, so this is initial, this is final. So initial is 12 meters per second in that direction, final is 0. It's asking you what average force is exerted by the gun. Okay, now you can apply the one-dimensional kinematics to solve for this guy. Okay, meaning you can solve for the acceleration first and then doing the mass times the acceleration to give that. So because basically you know the V prime, that should be equal to V initial, or V initial is V plus acceleration. Or actually, I think you are going to use the last equation from the equation of motion. So final square equals to initial square times 2 times acceleration times d. Then you can solve your acceleration, okay, which will be final prime square minus initial square divided by 2d, okay? And once you have your acceleration, then the force can be calculated by doing mass, the capital M here in this case, times acceleration. Okay, so you can calculate the average force by doing that way. Or now there's a couple of different ways. Okay, so this is the first way using kinematics and second law of equation plus second law, Newton's second law. Okay, you can do it that way. You can actually also do conservation or work energy theorem. So average force times the distance traveled, that should be equal to the kinetic energy change. Okay, so 1/2 mv prime square minus 1/2 or capital M v initial square. Okay, so then F is equal to, so this guy is 0, final is 0, that goes to 0. Okay, so just minus 1/2 capital M v squared divided by d. Okay, minus 1/2 1.00 kilogram times v minus 12 meters per second square divided by d 20 centimeter. You want to convert it into meters. Okay, so 0.2 meters. So then average force is equal to minus of 360 newtons. Okay, all right. Of course, you can apply it different ways. If you have another ways of solving this, okay, that's fine. So lastly, the part C says compare this to the force exerted on the gun if the bullet is accelerated to its velocity in 10 milliseconds. Okay, so this is like assuming if there's no mechanism of reducing the recoil force here. So that means if this guy strikes at this end directly instead of 20 centimeters over here, it just over there happens over there, and then the impact time when this is fired, it takes is like the 10 milliseconds. So then what will be the force? Okay, so then you are going to use as the average force times delta t impact time, that should equal to the change in momentum. So it'll be capital M v prime the final minus capital M v initial. Okay, so then your average force should be equal to capital M v prime minus capital M v divided by delta t. Okay, so 1 kilogram times final will be 0 minus 1 kilogram times the initial was 12 meters per second. Okay, and divide by delta t of 10 millisecond, 10 times 10 to the negative 3 second. Okay, so then what will be the speed here? So average speed here will be equal to, when you calculate this, it's going to be 1200 newtons. Okay, and then with a negative sign. Okay, all right, so then you can see it's actually much larger than this, right? About 3 times more than that guy. Okay, so you can actually reduce the recoil force by having this mechanism. Okay, any questions you guys might have? All right, so if not, then we are going to stop here for today. Okay, so I'll see you guys in lecture on Monday, and then the Friday lab attendees on this afternoon. Okay, bye guys.